to take an interesting approach here. There's a lot, obviously, to talk about with distributed architectures. However, what I want to talk about really are those elements that make up distributed architectures and why distributed architectures are so hard. Because they are. So let's actually find out why they're actually hard. When we talk about architecture styles, there's really two kinds of branches, two kinds of categories. Those monolithic type of architecture styles. Those things, for example, like layered or modular monolith, microkernel. When I say monolithic, these architectures are typically single deployment units. When we make a change, we deploy all of that code as a single unit. But on the other side of the classification, we have distributed architectures. Those things like microservices, event-driven architecture, service-oriented architecture. Yeah, it's still out there. Space-based, maybe it's service-based. And this is what we're going to talk about, this area right over here with distributed architectures. There's a lot of decisions you have to make with distributed architectures. As a matter of fact, we're going to cover 9 of those major areas in this next hour. So I'm going to talk really fast. So what I want to do is briefly go over all of the complexity that exists with distributed architectures that we don't have with the simpler monolithic architecture styles. But then, I want to show you some interesting things. We're going to take a little deep dive into some of those really hard aspects to kind of show you some interesting parallels and synergies between some of these. Okay, so we'll dive into some of these. But what I really want to do at the start is show you what these elements are and some of the complexity and choices that we face. And the first one, when we start talking about distributed architecture, is which one? Which one of these would be most appropriate for our next system or our migration for that matter? And it turns out each of these architecture styles has its own set of superpowers. But it also has its own set of bad things as well. As a matter of fact, in our book, The Fundamentals of Software Architecture, Neil Ford and I created these star ratings that you'll see in a little while in this session, where 1 star is a characteristic that's not well supported in that architecture. A good example would be something like high scalability in a modular monolith or high scalability in a layered architecture. Other superpowers are things like, for example, high elasticity in space-based. That's what it's built for. However, like I said, 1 star is kind of not well supported. 5 stars is very well supported. We could use these as guidelines to kind of direct us towards which architecture style might be best suited. And then what I'm talking about here is really about those trade-offs. The good things about it balanced with the bad things about it. As a matter of fact, it's not just the architecture style. It's what kind of database should we be using? As a matter of fact, even if you have an existing system, is it the right kind of database? Because it turns out that in distributed architectures especially, we've got a lot of choices. There's the typical relational database, for example. Maybe we're using key-value databases. We could be using document databases like MongoDB. Could be column family databases like Cassandra. We have graph databases and also NewSQL. Isn't it interesting? Like those architecture styles, each of these databases have their superpowers, their strengths, but also their weaknesses as well. And so we're going to be revisiting 2 of these. We're going to look at the synergy between the style and the database and see some very interesting things. But before we launch into that, let's take a look at some of the other kind of complexities, the elements that we face in distributed architecture. Another common question we have is, especially during migration, and I touched on this a little bit in my last session, is what do we do about the migration pattern? How do we actually migrate our applications? Should we use tactical forking, or should we use component-based decomposition? Now, each of these have their own set of trade-offs. Tactical forking is where we actually replicate the application, actually copy the Git repo, or whatever repo we're using, to another team. And this team's using the original application, and we copy it again. And we all start acting as sculptors who start chipping away at what we don't want. It's all about replication and deletion, just like taking a block of marble and sculpting it. It produces really horrible results, but it's really fast. But then we have component-based decomposition, something I'm actually going to be spending an entire session on Friday at 4:30. And these are a set of patterns where we can actually migrate an application through controlled, iterative refactorings with fairly low risk. But this is all about extracting components to create services. Which one's better? Again, in answer to all of these, it depends. However, there's the trade-offs associated with these two choices. Well, another choice that we may have, and as a matter of fact, if you're working in distributed architecture, all of these are going to be questions for you. The other thing is about service granularity. What size should the service be? Should it be small? But what are the implications if I start breaking things up into really fine-grained services versus those coarse-grained services? Again, I touched on detail, spent half the session this morning, well, I should say earlier this afternoon, actually talking about the drivers, about service granularity. Those type of drivers that say we should break things up based on maybe code volatility, or maybe scalability, throughput, fault tolerance, access control. These are good things we can measure to tell us to break apart services. But there's trade-offs. When you break apart a service, you no longer have database transactions. We can't do commits and rollbacks anymore. So while we get some of those benefits by breaking it apart, the trade-offs for this element of distributed architecture is really that lack of data integrity and data consistency. We also have to worry about the database. We start breaking apart our services, but then we have to correspondingly break apart our data. That's hard. And sometimes it doesn't work. And also, what if these services all need to talk to one another? Things will be slow, and we lose that fault tolerance. These are all trade-offs that we have to balance between what I call granularity disintegrators, breaking apart a service, and integrators, putting it back together. This is a very hard decision to make. Okay. Another element of distributed architectures is code reuse. This is a reality. Because when we break apart systems or even start doing greenfield, these don't matter whether it's migrations or starting a new system. If we are doing distributed architectures, we will have shared code. It is a fact of life. It's the proper way to do software development. So if all of us sitting in this room, all of us are all an individual microservice, where do we put our string utilities? How about logging? How about auditing? How about all those date utilities, calculators, all that stuff that all of us need? Where does that go now? Well, we've really got two main choices. There's four, but two primary choices. And that is, well, we could make it a shared library, like a jar or a DLL, and all of us just use that code when we go to build and deploy. So it's statically bound to us. Or we can create a shared service out of some of that, such as, for example, authorization. Gee, should that be a shared service? Or should authorization be a shared library that all of us use? I mean, how do you make these hard choices? And the answer? It's about analyzing those trade-offs. The fact that with a shared library, a jar, a DLL, a gem, a package, any of those artifacts, depending on your platform. Well, the nice thing is, let's go backwards. Let's make authorization a shared service. So I'm going to the authorization. All of you need to call me to make sure that that user is authorized for that request. So what if I walk off stage? Uh-oh. All of you might as well leave the auditorium because you can't work. Well, what if all of a sudden I kind of slow down a bit and can't get all of your requests done in time? What if all of you start scaling and I just get like, oh, that would be even. You know what? That would be fun to do. So I should, if I had 90 minutes, I would walk off stage. But how about this one? I would like all of you at the same time to ask me a question. Ready, set, go. No, don't. But do you see, that would overwhelm me. And none of you get your questions answered. That's about scalability, fault tolerance. And how long is it going to take all of you in the back row to walk down here to shake my hand, which is our communication point? It's going to take a while. Performance. Yeah. If I change my boots right now into sandals, I may break all of you because that's a runtime change. All of a sudden we're like, whoa, forget about shared service. Because think about it, with a shared library, I don't have any of those problems because you're bound to me. This is compile time. I mean, we're together in your deployment, in your pod, wherever you happen to be deployed. I'm with you, right beside you. We can hold hands the whole time. However, what happens if I constantly change? Every one of you have to constantly change. It's a lot of churn. Yes, we can try to version. Yeah. Neil Ford and I coined, most of you might be familiar with the 8 fallacies of distributed computing, something else that plagues us here. Neil Ford, and those were coined in the mid-90s, by the way, by Peter Deutsch and some other folks from Sun Microsystems. Neil and I started to coin beyond the 8 fallacies. We coined fallacy number 9 of distributed computing. Versioning is easy. That's a fallacy. That's something you might believe to be true, and it's not. Yes. You wonder what fallacy 10 of distributed computing is? Are you ready? This is the other one we coined. Compensating updates always work. Isn't it funny? We think about distributed transactions, which we're going to talk about in a little bit as well. And we look at a distributed transaction. Well, if I'm going to coordinate these 4 gentlemen in the front row here, I make a request, commit, request, commit, request, commit. These are all commits to individual data. I go to invoke you, and we get an error. Oh, what do I do? Well, I have to reverse your transaction, reverse your transaction. It's called a compensating update or compensating transaction. Fallacy number 10, compensating updates always work. What happens if the reversal fails? Now we're in a big mess. That's why it's a fallacy. Yes, it doesn't work all the time. Anyways, but fallacy number 9 pertains here because now I have to do all that version management and a lot of churn. What happens if this is Java, this is .NET, and we're doing some Perl code? How many versions of me do you need? 3. Yeah, so you can see there's trade-offs involved with this. Every one of these elements of distributed architecture have these kind of trade-offs. This is why it's hard. Okay. So isn't it frustrating? On all of these 9 that we're going to see, I can't give you an answer of which one to do. No one can. Google can't. ChatGPT can't. Because it requires trade-off analysis. Okay. Contracts is something that we require in distributed architectures. I have to talk to you. Should that be a strict contract? Things like JSON schema, XML schema, maybe a protocol buffer, an object, a Java object, a C# object. These are all strict contracts. Or should the contract be a loose contract? Oh, something like standard JSON, key value pairs, simple JSON without a schema. There's trade-offs between these about high contract fidelity versus brittleness. Because if I change a contract, I break every one of you. Oh, no, Mark, no. Just version it. Remember fallacy number 9. Versioning is easy. Same thing applies to contracts as well. But also, what about the high data fidelity piece? I know exactly what I'm expected from you and what you're expecting from me. But with loose contracts, I don't know. It's a string. It could be a number. It could be a letter. I don't know. But it's very, very flexible. And in most cases, versionless. Yeah. Now, it's interesting. GraphQL kind of fits right in between strict and loose contracts. But anytime you write a service, you have to make this decision as well. Because a lot of you just assume we're going to pass JSON back and forth. Maybe that's not the best idea. We have to analyze those trade-offs as well. Well, the journey continues because now we get to talk about how I'm going to communicate between services. This is all about communication protocols. Should I make a simple REST call between us? It's easy. Should it be asynchronous messaging? That's hard. Maybe gRPC, Google's remote procedure call, with protobufs and HTTP2 persistent connections. It's fast. Which one should you use? How do we answer that question? What are the trade-offs? Interesting. If I made a RESTful call to you to get information or to ask you to do something for me, I hope you're in the room, because otherwise, I can't speak. Yeah, we create a dependency, actually. It's not as loosely coupled as you think. However, make it async. I don't have to wait on you. I can tell you something or just put it on the seat when you return from wherever you're going there to get some water or something. I'm still doing all my stuff. That's a lot faster and a lot more decoupled, isn't it? Except, how do I know you got that message on your seat? Yeah, what if you get an error? What if you can't read it? I've already left the audience. I've already left the stage. And you're like, wait, I can't make out these words. Hey, Mark. Oh, Mark's not here anymore. Error. Yeah. What about gRPC? Isn't this interesting? Google's remote procedure call. That's another option, isn't it? Because it supports provides 10 times better performance than REST. 10 times better performance. Well, you start to ask, wait a minute. You're telling me if I use gRPC, I can improve my performance by a magnitude 10 times faster? Yep, indeed you can. Well, we should be using it. Is there a trade-off for that high performance? Nope, can't think of one. So Neil Ford and I, in our book, The Fundamentals of Software Architecture, coined the first law of software architecture. And that states this: everything in software architecture is a trade-off. gRPC gives you 10 times performance increase. Well, I can guarantee you one thing. If you go to gRPC or gRPC-LB protocol pages, they're not going to tell you what's bad about it. We have to find that trade-off. It's there, and that is our first corollary to the first rule. If you think in architecture that you found something that doesn't have a trade-off, all it means is you haven't found it yet. It's there. Keep looking. Because that, folks, is a remote procedure call. That means I have a piece of your code. Think about that in microservices. I have a piece of your code. This is no different than .NET remoting or EJB, IIOP over RMI, any of those. Because the point is, we have stubs and skeletons in a gRPC. I'm invoking a method, and magically, behind the scenes, it's invoking you. What if you're not there? Oops. Yeah, as a matter of fact, if you're not there when I'm here, we have a problem, because that's a socket-level handshake, persistent connection. So the point is, what's the trade-off of that high performance? Tight service coupling. Oh, yeah, we don't want to do that. Now, that's how we make the decision. Which is more important to us? Super high performance or loose coupling? Yeah, all of these have these kind of trade-offs. Another element that we have to make a decision on in any distributed architecture is workflow. We have to coordinate multiple services. Should I use orchestration or choreography? Why? I don't know. Do we have to answer that? Yes, we have to answer it. You can't move forward without it. What is the difference anyway? Here's a great way of thinking about the two. Look at that word, orchestration, right there. What word do you see embedded in there? Orchestra, yes. Go to any symphony, go to any concert. What do you see? A conductor, exactly. All the musicians are doing their own thing, playing one, maybe two notes max. I play the violin, I could do a double stop and play two notes, but it sounds like one. So let's all say we're doing one note. Well, my violin does not make a symphony, trust me. But the conductor brings all of you together to make that beautiful music. Yeah, that's orchestration. But what in life have you seen that's choreographed? Take that. What's choreographed? Dance, exactly. Yes, have you ever, let's say we got the stage here and we're going to do a beautiful classical or modern or awesome Indian dance. Is anybody directing you? That would look silly, wouldn't it? As a matter of fact, everybody would be like, what are you doing here? Just get away. We're doing our own thing here dancing. Yeah, all the dancers are just communicating and looking at each other to do that beautiful dance. There's no conductor. We're just all communicating together. That's choreography. It's a great way to keep in your mind the difference between the two. And yes, guess what? There are a lot of trade-offs between these. Great workflow control and state management with orchestration. Hey, I do play the violin. And let's say I'm in an orchestra. We're playing, and I've got a 27 measure rest. It's 27 measures. I got to go 2, 3, 4. 3, 2, 3, 4. Oh, this is boring. 5. Was I at 4 or 5? I'm lost. I have no idea where we're at in the music because all it shows is a bar with 27 on the top. I'm in panic mode. What do? I got to start playing sometime. I make eye contact with the conductor. Because who knows exactly where we are in that music at any given point in time? The conductor has the entire score, knows exactly what note we are on. That, everyone, is the orchestrator. That orchestrator knows exactly the state of that workflow. It controls that workflow. It knows how to do error handling in case all of a sudden one of the pieces of the stage falls down and we lose all the wind instruments. Well, we're going to keep going. I don't know what we're going to do, but it's the conductor, it's the orchestrator that does that knows. You guys play? Ready? You guys play. I don't know how to conduct. And then you guys play. You guys stop. I know exactly the workflow of this music. Yeah. What about choreography? Where's that workflow? All of you are separate services, no conductor. Okay, I'm going to make a request. Tell me Tell me your favorite city in India. And all of a sudden, but you have to ask around to get a poll. What's that workflow? It's completely distributed. It's everywhere. Yeah, so we have little or no control over the workflow, nor error handling. But choreography is fast, and it's highly scalable, and it's decoupled. Orchestration is not. These are some of those trade-offs between making this kind of decision as well. And yes, you do have to make it. You have to make it. Oh, boy. There's another one, too. Boy, it just never ends, does it? Actually, if we had 3 hours, we would do 25 different elements of distributed computing. This is all about distributed transactions. Should they be atomic or eventually consistent? What does it even mean to have an atomic transaction in a distributed architecture? Because we don't have ACID transactions. We can't do commits and rollbacks against a request that's going across multiple services, regardless if we break apart the database or not. An atomic transaction in a distributed architecture is one that's placed at the request level. I'm going to show you 8 different ways of doing this in just a little bit. I better hurry. However, what it means is we've got a workflow, and everybody's doing commits and stuff. I have to wait until that workflow's done. Oh, let's do an example. Here's a good example. I want to place an order. I'm a customer. I'm going to place an order. As a matter of fact, let's place an order. What do you want to buy? Let's buy some water for everybody. Okay. All right. So what do I have to do? There's 3 services here when I go to buy some water for everybody. So I'm going to buy 400 cases of water. Okay. So what do? I place the order. That goes to an order placement service. That validates my order that I just placed right here. It generates an order ID, inserts the order into a database, but then I have to pay for it. So then that order placement communicates with the payment service. It charges my credit card. Then what has to happen? The inventory, 400 cases of water, needs to be decremented. That happens by inventory management. I'm meanwhile waiting for all this. And order is placed. There's my order number, 123. Fantastic. What happens when things don't work? Atomic transactions. Okay, place an order now. Okay, so just place the order. I'm waiting. Order's placed. Payments applied. Inventory service is down. An atomic transaction says even though it's distributed, I, because I'm the request, have to wait until everything is rolled back. But we don't have rollbacks. Issue a compensating update here to payment, reverse the payment, remove the order from the database. And then, and only then, do I get error, please retry. That's an atomic transaction. It's at the request level. What's eventual consistency then? Because that's the other side of the coin. Let's do that same scenario, because I like doing things concrete as opposed to waving my hands with service A and service B. Let's place that order. Ready? And it's going to fail. Okay, 400 cases, go. There's my credit card number, go. Okay. Order's placed. Boom, perfect. Payment applied. Inventory failed. Error. Did you notice what the difference was? When an error occurs, I get to leave because it's not atomic. Eventually, we'll clean everything up, but we're not going to wait for you. We're not going to make you wait. So with eventual consistency, the transactional boundary is around each service, not the entire workflow. Oh, wait until you see this, because I'm going to show this in detail. Okay. Well, that is our journey, everyone. Those are the elements. Some of them, the more significant core ones, that we have to make decisions about. Every one of those. Well, something interesting I want to show you about these now. Let's dive into details on some of these because this will fascinate you. So let's review some of them we looked at. For example, what about the things like, for example, the type of migration that we use? Maybe it's the shared code. Do I do a service or a library? Maybe it's the contract, service granularity. I put those in boxes because largely those can be made independent of other decisions. However, isn't it interesting? There's a relationship, a synergy between the architecture style and the database type we choose. These are related. They're not independent of one another. However, the real magic, everybody, is what Neil Ford and I discovered when we were writing our book, Architecture, the Hard Parts. It turns out workflow, communication, and transactions are all interconnected. This was a major, major discovery that we made and refined. What I'm getting at is this. You can't make a decision about a database independent of the type of architecture style you're using. One impacts the other. You can't make a decision about going sync or async without impacting the workflow and transactions. All of these are interrelated. They're all moving parts, and I want to show you each of these. Now, due to the time, I can't go completely in depth on all these, but I at least could show you an example of one. So we saw on architecture types, or the architecture style. We've got 4 main architectures. Of course, there's all hybrids of these, but these are the 4 core. Microservices, service-based, event-driven, and space-based. And they all have strengths and weaknesses. Interesting. Let's focus on some of the core operational things that all 4 of these do well. One of the reasons we probably want to move to a distributed architecture. Better fault tolerance, better scalability, better performance in some cases, not all. But these are operational considerations that distributed architectures do well. Here's all the databases I showed you. Somewhere, there they are. These have some things that do things well and not well. As a matter of fact, here's the operational concerns here. Each database has its strengths. Some are available, some are not. Some have high throughput, some do not. And here's the key point. If you're choosing an architecture style for that high scalability, and your database doesn't scale, it's probably not going to work. These can't be made independently of each other. Now, I will say the choice of a database type is largely dependent on the kind of data we have. If I've got name-value pairs, that's how my data looks like. I'm probably going to choose a KV database, a key-value database, because that matches. Now I'm talking about domain isomorphism. The shape of my data doesn't match the shape of the database. Name-value pairs in a relational database. What do you think? Yeah, oil, water. Yeah, that's taking a square peg in a round hole. Nope, doesn't fit. Yeah. These are the kind of things we're talking about with the domain. So that usually drives us towards a particular database. I need extremely fast read capability. Neo4j, graph databases. That's what they're built for. So, isn't it interesting? If we don't match these up, things generally won't work. Let's do an example of one of these, because I can't go through all of the architecture styles, but at least I could show you one, microservices. Well, what databases associate well with microservices? How do we answer that question? We look at the characteristics that microservices supports. Fault tolerance, 5 stars. probably the highest of any architecture style, because of the fine-grained function-level nature of a microservice. Micro means small in terms of what it does, not its size. Scalability, 5 stars, because we're scaling at a function level. Performance, whoops, yeah, not very fast, because of all the latency of communicating between small services. Yuck. Network latency, security latency, data latency, all of those things. But let's take a look at our databases in terms of scalability, which is the first one here, and availability and partition tolerance, fault tolerance. Oh, what do you think about RDBMS, relational databases? Square peg, round hole. That's pretty high risk. Now, again, remember, it's largely based on domain isomorphism. Isomorphism means, does the shape of one match the shape of the other? No. Well, in case of relational data, yes, I need a relational database. This is what this analysis does. It shows you, yeah, you can use a relational database with microservices, but it's risky. Why do you say it's risky? Because it doesn't scale and it's not partition fault tolerant. Microservices is. If that's what you're striving for and you've got relational data, it's not going to work well. There's high risk there. Oh, what about a document database? Because most of what we do is store JSON objects. Okay, so that's the domain fit, but it's pretty high risk with microservices. Why? Scalability and throughput are a little bit better. But we're not talking 5 stars. It's not going to be able to scale as well. It's not going to be as available as we need it to be. Now, I'm not saying not to use it. What I'm saying is it's risky. There's risk we need to mitigate. Oh, what about a graph database? 3 stars, and these are all in our Architecture of the Hard Parts book. So if you're wondering where these stars came from, why they are, these are all in our chapter 6, I believe, of our Architecture of the Hard Parts book. But the point is, what about a graph database? 3 stars for availability, 3 stars for scalability and throughput. You know, it's kind of average. You know, I put this actually at medium risk. This is why. Graph databases help mitigate the really poor performance associated with microservices. Yeah, so this might be okay, medium risk. Okay, what about key value? Oh yeah, very low risk. That scales and is highly fault tolerant, as are columnar databases like Cassandra, for example. What about NewSQL? Kind of in the middle of the road. That would be about medium risk then, I'd say. We still get relational, but we also get scalability. Kind of plays both sides of the fence there. This is the kind of analysis we can use to see that some of these decisions, some of these elements are truly not independent of each other. One will impact the other. Have I convinced you distributed architecture is hard? This is not easy stuff. Okay, but we have 20 minutes left. So what I want to do is actually show you one of the most interesting discoveries we made in our book. And that is these 3 pieces right here. So it turns out if we look at those 3 things, distributed transactions, communication, and workflow, what we started to realize as we were working through all this stuff, if you change one, it impacts the other. We call these, Neil and I call these, the 3 primordial forces. How can we simplify distributed architecture? How can we simplify our decisions? It's things called transactional sagas. Let me show you. Distributed transactions is all about consistency. And we have 2 choices, atomic or eventual. Communication, we could do synchronous or asynchronous. Now, there's a lot of different types of communication, but they both fall within those 2 categories. And what about workflow? Workflow, we had orchestration or choreography. Well, there's 3 primordial forces. Each are a binary. So if we do basic math, what does that mean? That means there are 8 possible combinations of these 3 forces. That was our discovery. That just by making something async does not improve performance. Yeah, it does. Nope, I will show you why it doesn't. Because it impacts the other things. So, if I look at a summary here, and I'm going to go into details on this, this is a chart that Neil and I put together to say, well, based on these combinations, atomic transactions, synchronous, and choreography, well, what are the characteristics of that saga? Now, a saga is a story. It's a transaction. It's the way you build distributed architectures. And it turns out that these sagas are the core crux of how you design a distributed architecture. All the other stuff are all kind of the complex detail stuff. This is how you start. Well, Mark, there's 8 of them. How do I know? Well, what's most important to you? Well, for us, it's time to market. We have to get our changes out faster than our competition. We have to get new features and products out faster than our competition, because if we don't, we lose our competitive advantage and we close our doors. That is our most important thing. Well, look at this chart right here. I would say probably complexity most aligns with that. Certainly isn't scalability, certainly isn't responsiveness, it's not coupling. No, really has to do with complexity. The more complex a system, the longer it's going to take for us to get those changes out, correctly even. Well, red is bad, green is good. I know I haven't had a chance to change these yet. I humbly apologize if you're like, they all look yellow to me. I apologize. Okay, 1 star or 1 circle is okay, 2 is either really good or really bad. Let's take a look at the complexity row. What do you see here? 3 greens. The rest are yellow and red. We want something as simple as possible. I see 2 greens right here. That's the fairy tale saga, which I'm going to show you in just a little bit. Well, what is the fairy tale? Eventual consistency, synchronous communication, orchestration. Boom, there we go. That's probably what I should look at first, because that's going to give me the best time to market. Yeah, isn't it interesting? So let's actually take a look at each of these very quickly. Now, I do believe Neil Ford is going to have a talk where he actually goes into these in much more detail, because in 15 minutes, I'm going to be showing you these at about 1 a minute. But it just gives you kind of an idea of what a saga is and what it's about. So let's take a look at these. The epic saga. This is named epic. And by the way, Neil and I had a ball, a lot of fun naming these sagas. That was actually the funnest part here. What is an epic? Well, it's a long-running historic novel. Homer's Iliad or Odyssey, that's an epic story. It takes 2 years to read. Yeah. So the point is, what do we have in our dimensions? Well, look at the transaction boundary. That's what the dotted line means here. These are all in our book as well, but this helps explain it a little better. That dotted line represents the transaction boundary. It's at the request level. If there's an error, folks, I'm waiting. You cannot end that request unless everything is consistent, period. You're going to hold me up and probably time me out. That's an atomic transaction. It's also synchronous, probably RESTful calls. Also, there's an orchestrator, a conductor. But if we notice, here is what results. A lot of red, high coupling. As a matter of fact, complexity is the only good thing here. Actually, everything else is red. Let's move some of these slider bars over. Let's move communication to async, because what is the problem here? It's too slow. Responsiveness is red. Scalability is bad. How do you increase scalability and responsiveness? Make it async. That's what teams usually do. Well, what happens if we make it async? Look at responsiveness. It just went from green to red. Yes, as a matter of fact, this is called the fantasy fiction. Now, this is a complex story. It takes place 4,000 years from now. It's really hard to believe. Yeah. So notice, this is all red, everybody. We've improved some of the red, 2 dots to 1. But the point is, here's why it's bad. That atomic transaction is what kills us. Even though it's async, because it's atomic, I have to wait for errors to get fixed. But because it's asynchronous, I have no idea when they will be fixed. That's what starts driving down responsiveness. But it is asynchronous, so I can run everything in parallel and controlled through a conductor. Well, why don't we do this? Let's change around some of these things, and let's actually now make it atomic or eventually consistent. But let's go back to that synchronous, because, yeah, async didn't work. So what do teams do? They say, whoa, async just made everything actually worse. It wasn't because it was async. It was because of the other 2 factors. So now, isn't this fascinating? We think about these individually, and you can't, because just by thinking about communication alone, we've now messed things up completely. So let's go back to synchronous. Let's make things eventually consistent. Now we get the fairy tale saga. A fairy tale is an easy story. It's a pleasant ending. Oh, the prince and the princess ride off into the sunset. Oh, tears coming down my eye. Yes, this is okay. Look at all the green. Complexity. 2 green dots. This is easy. This is the easiest one. It is the easiest combination of these 3 forces: eventual consistency, synchronous communication, and orchestration. Well, I like it, but it's not quite fast enough. So what do? Make it async. Yeah, thank you, ChatGPT. So notice it's synchronous here with the orchestrator, but let's actually go ahead and make that async. And what do? Well, I bet you're all waiting and saying, yeah, what's it going to look like now? And we get something called the parallel saga. The parallel saga is eventual consistency, asynchronous, but still orchestrated. Look at the transaction level here. Transaction level is no longer atomic. It's at the service level here now. And so the key point is, I don't have to wait. That's why responsiveness is so good. But also it's asynchronous, still controlled by an orchestrator. Parallel saga is pretty good. As a matter of fact, look at the ratings here. 3 green dots. The only thing negative about this really is about the complexity. Yeah, async and eventual consistency. The 2 of those make this somewhat complex. Well, okay, enough of this. What about choreography? Let's try some of that and see what might happen. Well, let's go all the way back to atomic sync, and let's try now choreography. And this is what that architecture looks like. And by the way, isn't it interesting? We can form hybrids here, but these are the 8 possible combinations of architectures. We can optimize parts of it and stuff like this, but these are the 3 forces that make up a distributed architecture. So we call this the phone tag. Has anybody played that child's game, the phone tag? You whisper something into somebody's ear. Whisper, whisper, whisper. And then you'll tell somebody else. And you keep going all the way through, and let's see what it ends up with at the end. It's a fun child's game because it never ends up correct. Somebody messes up a word, and then that word gets messed up. If you haven't ever tried it, do it tonight. It's kind of fun with your friends or family. It's kind of fun. It's like, hey, let's play phone tag. Anyways, the reason is because look at the shape of this. Request comes in, it ends up talking to another service, talks to another service. It's atomic transaction. But the point is, it's like the game of phone tag. I'm passing data to you, you pass it over here, you pass it over here, over there, and eventually it gets processed and back to me. This is very close to what is known as the pipeline architecture, or the pipes and filters architecture. Pass it over to here, pass it over to there, just like phone tag. Okay. But it is synchronous, which makes it bad. And choreography, which is hard, because we don't have that workflow control. Okay, so notice here, what did we do? All we did from the prior one was actually say, well, let's try choreography instead. And look what we did. We turned green into red. But it's not because of choreography. It's because of the other combinations of those. Well, this didn't work. Well, what can we do to improve this? Let's make it async. There has to be the worst combination possible, right? And here it is. It's called the horror story. This is the worst possible story you will ever read. We call it the horror story because it contains the three hardest pieces, three hardest elements of distributed architecture. Atomic transactions, extremely difficult. Asynchronous behavior, extremely difficult. Choreography, a lot more complex than orchestration. Now, here's an interesting story. Neil and I saw that there's the 8, and we started to name these. We had fun naming this one. We said, and this was during when we were writing the book, because this went into the book. We said, we ought to not focus on all these, because some of these will never happen. I mean, these are theoretical. This is a mathematical combination. No one would ever use this. And I said, yeah, Neil, you're right. We should just think about our experiences, client sites that we've been at and are at, and we should drop some of these off and simplify this. Yeah, you're right. 2 weeks after we coined this, Neil was at a client site that encountered the horror story. Yeah. As a matter of fact, Neil and I have found all 8 of these in the wild. These all exist in production systems. The horror story comes about because this is really about the epic, isn't it? It's the epic, but we make it async to make it faster. That, and by the way, choreography, let's try that. That's where we end up with the horror story. It's the best of intentions without the understanding that these 3 elements are all tied together. You can't change one without thinking about the others. Okay. Well, how do we improve the horror story? Oh, don't make it atomic. Go back to eventual consistency, synchronous, and we get time travel. Now, this is like a story that moves through time. Notice the transaction boundary. It's in each service here, which means I did my story, now it's your turn, but if an error occurs, we're just going to figure it out later. Now it's your turn. This is kind of like a time travel story. It's synchronous in nature and also choreographed. We improved things significantly, though, from horror story, didn't we? One of the cool things about this, and you have all the slides now, so if you look at it, you can see the before and after impact of these. And we went from almost all red to green. So this is an improvement. Let's change one other thing, though. Let's actually make this async. Now we get the last one. We call this the anthology, a loosely associated group of stories. 97 things every software architect should know. Fantastic book. But it's just a collection of all of us experts giving you 1 page of advice. That's an anthology. It's where you devote a chapter or 2 to something like this. Notice, it's still choreography, but now I'm doing a handoff to you, and I don't have to wait anymore. You do a handoff to him. You don't have to wait anymore. If you get an error, it's eventually consistent. It's up to you to fix. Yeah. And look at the ratings here. 2 stars, 2 green dots for coupling. This is highly decoupled, a little complex, great responsiveness, great scalability. So what can we learn from all of these elements, all of these different pieces? Let's come back and see what we can learn. Because I'm going to come back to the summary now. Well, one thing we can say is, by the way, here's a best practice. Never use orchestration. Why? Look, orchestration. Look at all these dots here. They're all red. Orchestration's bad. Oh, yeah? Look at this one. This one's orchestrated, and And it's got 3 green dots. Orchestration is not bad. No, use it. What makes it bad is the combination of the other 2 forces. That's the secret. You can also use this summary to say, for example, I need high responsiveness. Just look at this summary chart right here. Okay, so it's going to probably be parallel saga or anthology. Those are going to give me that high responsiveness. Anything else, all those combinations, is not going to. So that means parallel saga and anthology. But notice, it's already made the choices for me. It's made a complex thing like distributed architecture just a little bit easier, because I know I've got to shoot for eventual consistency. But it's not eventual consistency that makes it responsive. It's the combination of eventual and async. And now it leaves me with a choice. I could do either orchestration or choreography. Choreography will be a little faster, but I don't have control over my workflow. Oh, no. We need central control of our workflow. Okay, choose parallel. It's still responsive. It simplifies this complex thing just a little bit better. And there you have it. Those are 8 primary elements of distributed architecture. But we did see a 9th, didn't we? And that was those transactional sagas. This, I get very excited about. I think it's actually revolutionary. Because how many of us have made these 3 choices independent? And all of a sudden we realize we're not getting what we think we're actually getting. We're making things worse. So, distributed architecture, everybody, is really hard, very hard. And it's understanding the trade-offs between all of these elements, applying our context, what's important to us, that will help us make all these mandatory questions. You have to address all of these if you're doing distributed architecture. All right, thank you all so much. Thank you.